Now we're going to address molecular vibration, which is called to physics the simple harmonic oscillator. The deal is that we've been dealing with diatomic molecules as a good model. We just dealt with rotation, and we're going to stick with it. So we've got a mass m1, a mass m2. The reduced mass of the system is m1, m2 over m1 plus m2, always the product divided by the sum, so that the mass, the reduced mass comes out with units of mass. And now our stiff rod connecting these two masses is instead a very stiff spring. So Slinky's turning into a spring now. The distance between the bond center, but the bond length, we're going to call x naught here. And the deal is that the force is minus some constant k times the term x minus x naught. And this is called Hooke's law. And that minus sign is important because if we think if x grows, then if we're extending the bond length, and the force is going to be to make x get smaller. If x shrinks, then we're compressing it, and the force is going to be toward making the bond grow. So it's what we call a restoring force. Now, to simplify the problem, in physics, this actually reduces to a basic problem where we put a mass on a frictionless plane, gotta love that, and we're going to put it at x equals 0 and stick the spring sort of infinitely far away with a force constant k, and then just say F is equal to minus k times x. So it just gets rid of dealing with that x naught. But the x naught is always implicitly in there, essentially as the equilibrium bond distance. So the question, if we're dealing with quantum mechanics, is always what's the potential? What's the potential energy as a function of x? And we have to remember that the force is the negative derivative of the potential, and that means that the potential is the negative integral of the force. So let's go ahead and do that integration. This means that v is now plus, because there are two minus signs, k times x dx. That's very easy to do. That means that the potential is 1/2 kx squared plus some constant c, but we're going to set that equal to 0. We're going to put the bottom of this parabola at a total potential energy of 0. So it's going to look about like this. We've got an x-axis. There's a 0. I go to 1 and minus 1. I'm going to go up 1 unit. I'm going to go 2 and plus and minus 2. I'm going to go up 4 units, and we make our nice little parabola here. So that's the potential, and it's got units of energy. So we have a parabolic confinement to the system instead of the square well that we've seen before. So it's a little bit different. The first derivative of the potential, again, is equal to the spring constant times x. That means the second derivative of the potential is just equal to k. And that's important to remember. So the second derivative, the spring constant, k, is just equal to the second derivative of the potential energy. So you're going to see a lot of time that we look for the curvature of the potential energy surface, and that is going to be, we sometimes call that the spring constant. We do lots and lots and lots of taking second derivatives of this potential energy surface, and we'll see this later on when we go to construct molecules. So that's very, very important. The spring constant k is the second derivative of the potential energy. All right, so now that we have a potential, let's do something with it. Since we have a potential energy, and that's now going to be, let's see, it's v is equal to 1/2 kx squared that we just derived. So let's solve the Hamiltonian. H psi is equal to E psi. That's the Schrodinger equation. But now that's minus h bar squared over twice the mass times the second derivative of the wave function, and there's a potential. Plus 1/2 kx squared times the wave function equals energy, total energy, times the wave function. So that's a little bit different. Let's rewrite this in the curviness form where we have psi double prime over psi is equal to minus 2m divided by h bar squared times the difference in the total energy and the potential energy. So that's the way that most expresses this curviness factor. And let's draw this potential again. So here's x, here's energy. We'll take some things off and set up a nice parabola. That's our potential, and we're going to have a potential and a total energy. So that's 1/2 kx squared, and here's our total energy. We're going to assume that there is some ground state solution to the Schrodinger equation. So this is going to be the ground state. So let's make some observations. First of all, the ground state is going to exist. Okay? That's typically a reasonable thing. And therefore, we kind of expect it to have 0 nodes, because that's what we've observed already. Also, there's confinement, so that the system isn't free to go anywhere. It's a little bit like the particle in the box in that sense, and so it has to have some curviness. So the ground state energy is going to be greater than 0, and there's going to be some curviness. So that's important, because we have to get some curvature in here. So let's have a look at this. Well, the confinement always shows up in terms of these things we call classical turning points. So where the potential and the energy are the same, we're circling it in red. And those are what are called classical turning points. That word classical is always important. And there, energy equals V, so E minus V is equal to 0. And that means that psi double prime has to be 0, assuming that psi itself is not 0. And let's assume it's positive, it doesn't matter. If psi is not 0, then in the curviness form of the Schrodinger equation, just up there, then psi double prime has to be 0, meaning that the wave function there is straight. Not flat, but straight. So let's go up from those turning points, and the wave function has to be in some way a straight line. And we're anticipating that it's going to be largish in the middle, because that's where the darn thing is supposed to be in the first place. So that's what the Schrodinger equation tells us should happen at the classical turning point. In quantum mechanics, when energy is equal to the potential, total energy is equal to the potential, the wave function gets straight. It doesn't necessarily go to 0. It just gets straight. So now in this classically allowed region in the middle here, the difference between the total energy and the potential is greater than 0. That's what we're used to seeing. And so the kinetic energy is greater than 0, and the second derivative has the opposite sign of the wave function. And we expect psi double prime over psi to be less than 0. And so since we don't think there are any nodes anyway, let's just top this function off like that. But there's more. So the thing is, the wave function now can sort of leak out of this classically allowed region. This is what we call tunneling into the classically forbidden region beyond the classical turning points. And so there, the energy minus the potential is less than 0. And that means since the total energy minus the potential is less than 0, the kinetic energy must be less than 0. You got it right. The kinetic energy is less than 0. It's kind of weird, but let's just go through it. That means that psi double prime over psi is now greater than 0. The curvature and the wave function have the same sign. And we can accomplish that here. We're above 0. We were curving down, and now we want to curve up. So we can curve up and just sort of make a nice smooth landing down to 0 there. And that does it. So that's something where the curvature is the same sign as the wave function. Instead of being a sort of a restoring function like it was inside, now it just smoothly goes down to 0 and all's good. And of course, it's going to do about the same thing on the other side, and we have a nice symmetrical ground state wave function. So that's what we expect the ground state wave function to look like. Now let's be quantitative about this. So now let's return to this vibrational ground state for the Schrodinger equation, but let's find the wave function quantitatively and the energy. So what we need is we've got this extra x squared term floating around from the 1/2 kx squared of the potential energy. So we're going to take a second derivative of the wave function, and we need something with an x squared times the wave function floating around. So let's assume the answer basically. So we also know that the wave function is this nice sort of top hat shaped thing, not top hat, but bowler hat shaped function here. So why don't we just figure that maybe the wave function looks something like an e to the minus x squared over 2 sigma squared. Why not? It's got an x squared in it. That might be useful. And that's a very well-known function. This is called the Gaussian or the normal distribution or the favorite bell curve for curve grading and everything else. So this is a very common function. It kind of looks like that green thing there. Let's give it a whack. So the first derivative is easy. We just poop out a derivative of everything inside, and we get a minus 2x from the x squared over 2 sigma squared, because that's just a constant sitting in there, times e to the minus x squared over 2 sigma squared, and that 2 over 2 cancels out. So we'd get minus x over sigma squared, e to the minus x squared over 2 sigma squared. Let's take another derivative. So let's see, we got one term that's going to look like minus 1 over sigma squared, e to the minus x squared over 2 sigma squared, and that comes from differentiating the x over sigma squared part. That's f prime g when we've broken this up into two functions. And then we're going to have another term. We leave, we're going to pull out another x over sigma squared, and so we're going to get that twice. We had one x over sigma squared leading the exponential, and another one comes out, so we're going to get x squared over sigma to the fourth times e to the minus x squared over 2 sigma squared. And that's an fg prime type term. This is the chain rule, where we take the derivative of fg, and it's f prime g plus fg prime. So let's take the curviness. Psi double prime over psi, that's minus 1 over sigma squared, because the e to the minus x squared over 2 sigma squared is psi, and it's sticking around. So it's just minus 1 over sigma squared, that's from the left-hand side of this, plus x squared over sigma to the fourth from the right-hand side of it. And there we go. That's the curviness. Well, that's kind of cool. Also, the curviness, remember in the curviness form of the Schrodinger equation, is equal to minus 2m over h bar squared, e minus the potential, which is 1/2 kx squared. So now we've got something we can work with. This is just the Schrodinger equation now, in the curviness form. So this means that 2m over h bar squared e minus 1 over sigma squared, I'm gathering all the terms that don't have to do with x on the left, is equal to km over h bar squared, that came from the 1/2 kx squared, minus 1 over sigma to the fourth, because I brought the sigma to the fourth term over from the left there, so it's a minus sign. That's all times x squared. So I've got a term on the left-hand side, which is just a bunch of constants, and a term on the right-hand side, which is a constant times x squared. Well, that's kind of interesting, because x can be any value. And this function is again one of these things where it's saying that the left-hand side equals the right-hand side, but the right-hand side has this free agent x, which can be any value at all. So I'm sort of able to scale this by anything, and that's kind of an interesting hint. The only way this can work, this always happens like this, the only way this can work is if the actual coefficient to the polynomial, in this case x squared, is equal to 0. And then it's going to be 0 equals 0 if that thing over on the left-hand side is equal to 0 as well. That's the only way I can get it to go, because I can choose any x I want, and if those things aren't 0, the fact that x can move around is going to make the whole thing not be equal. So the sort of, what is usually sort of the stupid equality of 0 equals 0, in this case it's great, because I've got two terms in a polynomial being equal to itself that can vary with x, and so I can just pull out those coefficients and set them to 0. So we've got these two terms that have to equal 0. Let's start with the right-hand side. We've got km over h bar squared minus 1 over sigma to the fourth equal to 0. And this I can solve for the width of the Gaussian. Sigma to the fourth is just equal to h bar squared over km. And so therefore sigma squared is equal to h bar over the square root of the spring constant times the mass. We need sigma squared, so we're going to leave it that way for the time being, rather than take fourth roots of anything anyway. So now we can take that into the left-hand side and solve the left-hand side. Twice the mass divided by h bar squared times energy is 1 over sigma squared, but we just figured out what sigma squared is, so that's equal to square root of km over h bar. That's trivially solved for the energy. This gives us the energy is 1/2 h bar times the square root of the spring constant divided by the mass. And that's also equal to 1/2 h bar times the square root of the second derivative of the potential. Remember, that's a really important way of representing this, divided by the mass. Well, it turns out that the classical simple harmonic oscillator oscillates with a frequency, nu, equal to 1/2 pi times the square root of the spring constant divided by the mass. Well, that 2 pi is easy to grab. This means that the energy of our simple harmonic oscillator in the quantum case of our vibration is equal to 1/2 h times the characteristic frequency, nu, vibration of the harmonic oscillator. Remember E equals h nu? Here's E equals h nu showing up again. There's just this little half out in front. So it's very important to realize that the classical oscillator always vibrates with the same frequency. You pull the string back harder, farther, it's just going to vibrate with more energy. This is exactly like a guitar string. You pluck the string harder and it gets louder. That's more energy, but the note doesn't change unless you bend the string. But basically the note doesn't change. You just get more energy if you pull it back harder. So the characteristic frequency is expected to be a very, well, characteristic thing of the system. Of course, classically you can have any value of energy, and quantum mechanics generally messes that up and doesn't allow that to be so. So in quantum mechanics, we're going to quantize the energy, and we've now found that the energy of the ground state, which we call the 0-point energy, is 1/2 h times the characteristic frequency, nu vib. And kind of the next question is, how about the excited states? What goes on for E1, E2, E3, E4, etc. If the first state we're going to designate with a 0, which in fact is true. So now we know what the wave function looks like. It's a Gaussian. We've solved for the width, sigma, so we know that. We know a characteristic frequency. We know the energy of the ground state. So we know everything about this ground state solution.